Thanks for the introduction, and it's my pleasure to be here. So I think some of you will have heard either Alex Wanscha, maybe Nancy or me give a talk with more or less the same title. So I'll try to say something new which you may not have heard before, if you've heard such a talk before. Also, this can be somewhat informal, so feel free to ask questions. I have enough material, I think, for more than an hour, but I can also spend more time on something or less time on something. Just let me know. Okay, so let me maybe start by recalling a little bit what I will need from string topology. So throughout this talk, M will be a closed manifold. If you want, you may assume it to be oriented and maybe spin when it comes to holomorphic curve theories. None of this is necessary if you're willing to work with twisted coefficients. But I will not go into such details anymore. Yeah, but everything is true without those assumptions. And I will also throughout denote by lambda the loop space of M. Smooth loops in M, where S1 just identify with R mod Z. So it's one periodic loops in M. And string topology, generally speaking, is about operations on the homology of loop spaces of manifolds. And for today's talk, I will be concerned with two operations, one product and one coproduct. So there's a product which has degree -n, and that is a so-called loop product. And that is doing the following. So we define it on the chain level. We take two families of loops representing two cycles in here. So here's my schematic picture of the first family of loops. Here's a second family of loops. So I'm just drawing one circle, but you think of it, it's a family of loops moving in the manifold. And then we have, they are parametrized loops. So we have time 0 somewhere. Yeah. Now we take the evaluation at time 0. That gives me a point in the manifold for the first family. In the second family, we also evaluate at 0. That gives some point in the manifold. And now we look at the locus where those two evaluations coincide. I'm just drawing it as a dashed line, meaning I'm taking the locus where those evaluations agree. And where they agree, out of those two loops, I can make one loop by going first around this loop. Now this is the same point as this one in the manifold, and then I go around that afterwards. So I get one loop again. So I get a new family of loops. And that represents again that's again, if those two are cycles, this will be a cycle again, and it represents a homology class, and that's the loop product. Yeah. So this was defined by Chas and Sullivan. And the other operation that will play a role today is a coproduct. So let's call it a loop coproduct. So this should be, I will denote it by lambda. So it goes So it should go from homology of lambda to homology of lambda tensor homology of lambda as a coproduct does. And we'll do the following. We start with one family of loops. Now we have evaluation at time 0, and we take some other time, which varies. So we take evaluation at some other time A. And then we look at self-intersections. So we look at the locus where the evaluation at time 0 and the evaluation at time A coincide. Yes. So, so you should imagine this loop being in the manifold and it self-intersects inside. So at time 0 and time A, the same point in the manifold. And then we can decompose the loop into two loops. Namely, we make it one loop going from 0 to time A. That is a loop because those 2 points are the same points in the manifold. And then we go from time A to time 1 or time 0 again, which is another loop. That gives me now a family of loops in lambda times lambda, and then we apply the König formula to view it as an element. Once we pass to homology, to view it as an element in the tensor product of homologies. Yeah. So I probably want to use field coefficients here to have a König formula at our disposal. Yeah, I will not be very precise about the coefficients we're using.
Is A fixed or are you relying?
No, A is varying. Yes. Which makes this product something of degree 1 minus n. This 1 comes from the freedom of A varying. Yeah, and minus n is the incidence condition on the 2 points. Right? Yeah, so you could define it with A fixed, but with A fixed you would get something which is essentially trivial. And the interesting one you get when A is allowed to vary.
What is? I'm a little bit worried about what happens when A goes through 0. It seems
yes.
like a loop swap.
Yes, that's why I left this little spots here. So let's look what happens when A goes to 0. Then let me draw it like this. So let's say 0 is here. So what we'll be doing, we'll of course you have a self-intersection here. So you'll go around the constant loop. Yeah, and then around the original loop. And likewise for A equals 1, you will get a similar picture where I'm drawing them in this order that here you go around the loop first and then around the constant loop. Yeah. And now this is bad because those are actually boundary terms that should not be there. If you started with a cycle here, then A equals 0 and A equals 1 will be actual boundaries. So what you get will not be a cycle, and it will not give you a homology class. Yeah. So this is actually not working. So the easy way to make it work is to just mod out all the constant loops. And there's still something to be done, but then it's kind of believable. Then those terms go away. Yeah, it's still not transverse. You need to do something, but still, basically, that's the way to get it well defined. So it will be well defined when you mod out constant loops, and that is how it was originally defined. It was originally defined by Sullivan, and then later again by Goreski and Princeton. Who studied this intensively and actually then more looked at the product dual to this one and studied its properties in relation to first year basics. Yeah. So now here's one of many puzzles in string topology that Nancy had collected over the years, which somehow didn't quite seem to fit. And one is that somehow lambda and mu should satisfy some relation. And I'll write you the relation. So mu and lambda should satisfy what we came to call Sullivan's relation because he first wrote it down. And I'll make a schematic drawing. I hate writing formulas, but you can translate everything into formulas. So this is my drawing for mu. This is my drawing for lambda. And when I'm drawing that, I'm coming from symplectic geometry or symplectic field theory. So for me, inputs are always at the top and then outputs are at the bottom. Yeah. So the operation should be read from top to bottom. So this is a product and this is a coproduct. So this means this is the operation lambda composed with mu. Yeah. Okay, so it's clear what these pictures mean, and then I don't have to write formulas. I think it's easier to read when you draw pictures. So this should be the same thing as the following. You first apply lambda, and then you apply mu on one slot, or you do it the other way around. So, and this makes intuitive sense. What does this mean? We take a loop product of two loops, and then we apply coproduct. So we take something which is obtained by taking a loop product, and now we apply coproduct. So we look at self-intersections. Now the self-intersections can appear either on this loop or on that loop. And that gives us these two terms on the right-hand side. Yeah, so just very naively, this is what you expect. Yeah, but then questions how. So is this true? And I mean, before it has any chance of being true, first of all, we would like to lambda and mu even to be defined on the same space. Yeah, because right now, so the problem with this one is that lambda is not defined on the full homology. So you actually do get boundary terms. Lambda is actually not well defined if you don't mod out something. Yeah, and I come back to what you really need to mod out. And also, now you could think, okay, let's just mod out the constant loops and pass the product to the quotient where we mod out the constant loops. It's also not working. Yeah, so we have examples that mu is not defined on the relative. If we have time in the end, I could show. Okay, yeah, there's some explicities. Well, maybe let me do it right now. Can I move to? Okay, I can. Yes, the example for. I mean, the first one I basically explained to you because of these boundary terms. Now, why does mu not pass to the quotient by the constant loops? So here's an example. Let's take Tn, the two torus would do, as a manifold, and do it just by drawing pictures. So let me take I want to define two homology classes. One homology class will just be Q0, some base point, viewed as a constant loop, as a zero chain of constant loops. Okay, in a loop space. Yeah. Okay, here it is. And that's gives me a homology class, a zero homology class. And the other one, I go in the x1 direction, and I take all the straight lines on the torus going in the s1 direction. So this is, let me call it C. So this is a chain parameterized by the torus itself because it can start at any point and then just go once around in the s1 direction. Yeah, so it's all loops. So it's going from the torus into the loop space. It's an n-dimensional homology class. So all loops. So not loops. I mean straight lines. In the x1 direction. Okay. And now I want to take the loop product of those two. So I need to look at the locus where the evaluations at time 0 coincide. Which means that, well, here the evaluation at time 0 just gives me Q0, this point. So I need to, so this singles out one unique loop which starts at Q0 at time 0. Yeah. So I get precisely this thing. Yeah. So the loop product mu of Q0 with C will be just let me call it maybe C0, this particular loop. Yeah, starting at Q0, going once around. Okay, so what I have a product of a constant loop with something which is living in non-constant loops, and the output is something in the non-constant loops. So the constant loops are not an ideal. So the chains in the constant loops are not an ideal for the product. And that means the product does not descend to the quotient by the constant loop. Yeah, because for the descending would mean that there should be an idea. Yeah. So that doesn't work either. And that was one of the starting points of our project, to see, okay, well, is there maybe some common space? And I will tell you today which space they can both be defined. And hopefully then maybe also satisfy Sullivan's relation. And we'll see that in some cases this works, and in some it's not tricky. Okay, so here's a question that I want to. So can mu lambda be defined on the same space such that Sullivan's relation holds? Another question is this part of some larger algebraic structure, this relation? Is there more to it? Yeah? Is it? And the third question I will address today is there some kind of duality Poincare duality relating mu to lambda dual. By lambda dual, lambda upper V, I mean the product on cohomology dual to the coproduct lambda. Lambda is a coproduct on homology, algebraically dual to a product on cohomology. Now, is there some duality between homology and cohomology, which is some kind of Poincare duality for loop spaces, which then moves mu to the product which is dual to lambda? Yeah. So this last question was the question that Nancy actually raised, and there's a nice story behind it. I don't know exactly when it was a couple of years ago. Nancy gave a math conversations talk here and listed all kinds of puzzles in string topology, among them these questions here, and in particular the last one about Poincare duality. And Alex Wanscher was in the audience and listened to that, and basically he took handwritten notes, sent them to me that evening, and basically the next morning we could answer most of that question, because it turned out that we basically knew the answers to a lot of those things from our work on rabinos homology, and that's what I want to tell you now. So there's one answer which is coming from a somewhat unexpected direction, namely symplectic geometry and rabinos homology. So let's completely leave this and talk about rabinos homology. Who of you knows rabinos homology? Okay, then it's maybe not a waste to at least write the action functional. So now this works more generally on any Liouville domain. Two-n-dimensional Liouville domain. And as usual, we denote by V hat the completion. And Rabinowitz homology is the homology of the action functional, of the Rabinoid action functional. It depends on the choice of Hamiltonian, I will specify in a second. It's from the loop space. Now, in this Liouville domain, times real numbers to R, and it's defined as the integral of lambda over x minus eta times integral 0, 1 x. This depends on some choice of Hamiltonian, and the Hamiltonian looks as follows. So I will always draw the schematic picture. This is my direction of the symplectization. So here's the boundary of V. Inside of here, we have V itself, and it's the completion. And the Hamiltonian should have as regular zero set the boundary. And then we just make it flat and extended. Completely will not matter what the Hamiltonian is doing away from the boundary. So this will be Hamiltonian H. And you can, critical points are as follows. So this gives us two equations. When we take you see, this looks like the classical Hamiltonian action, except that we have this real parameter eta in front of it. So the usual variation of the action functional tells us that the equation is x dot is eta times Hamiltonian vector of x. We just have this parameter eta in front of it. This gives us a Hamiltonian equation. And then if we vary this with respect to eta, we get the integral of h is equal to 0. Now, the first one here, we're choosing an autonomous Hamiltonian. The first one here tells us that we have conservation of energy. So h of x is actually constant, et, by conservation of energy, because of the first equation. Which means that this integral being 0 means that h of x is pointwise everywhere 0. Which means that I can also say that x is actually going from S1 to the boundary of V. So x lies exactly in the boundary, and it's a periodic orbit in the boundary.
So basically the difference is that in the standard case, you don't fix the energy, but you fix the period.
Yes.
You don't fix the period, you fix the energy.
Exactly. Yes. So I should of course mention this. Using this to build a Floer homology was the idea of was Poincare. And the motivation was precisely to study existence questions for periodic orbits of fixed energy, not fixed period. Yeah, and to try to do it directly rather than in the indirect way we've learned from Helmut and others to do, which I always thought a bit roundabout, because you want to find orbits on some energy hypersurface, and then instead you look at a problem with fixed period 1 and you work hard, and ultimately under some assumptions on the hypersurface you conclude you find them on the hypersurface. But it seems, yeah, so it was an attempt of kind of do it more directly. Yeah. And that works. So we find periodic orbits of given energy, and I take its energy level set here, this boundary. You could take something else also. Yeah, this works more generally. Okay, that's it's a periodic orbit, but we still have this parameter eta here. So there's still something interesting happening, because if eta is equal to is positive, then this orbit is running in the usual direction at some speed. Yeah. Run forward. If eta is negative, then it's run backwards. And eta equal to 0 is also possible. Then it just means that the orbit is constant. It's just any point on the boundary gives us a critical point, just as a viewed as a constant orbit with eta equal to 0. Yeah. So the critical points are all the periodic orbits in the boundary. Copies of them run backwards, and also all the critical points. There's no critical, all the points on the boundary. Of course, I need to perturb it by a Morse function, and it will be critical points of a Morse function on the boundary. Yeah? So it's kind of a strange complex. All right, so this is the definition. Now, and now, for it to be really useful for purpose of string topology, we want to rephrase this definition in terms of symplectic homology. So interpretation as so-called V-shaped symplectic homology. This is joint work with Alex and Urs. Actually, I want to call it rabinos Fleur homology of the boundary. Now, this is indicating that all the generators of the complex sit just in the boundary. Yeah. It does not mean that it only depends on the boundary. It does depend on the filling because you're building a Fleur homology. So you're looking at Fleur cylinders. Those Fleur cylinders might as well run through the interior, through the filling V. And it could depend on the filling. Yeah. So it's not meant to say that it depends only on the boundary, but we'll see that it's actually useful to denote it as something which is associated to the boundary. But some of the filling is used implicitly. Yeah. So this one is the same as some variant of symplectic homology, which is also associated to the boundary. And maybe, I think we don't need that. It's kind of unambiguous the way it's written, but it's using V-shaped Hamiltonians. So how is this? This is like symplectic homology, but we're using. Okay, let me maybe draw 3 pictures to remind you. So how do we compute symplectic homology? We're using these kind of Hamiltonians. We're using Hamiltonians which are linear, upward sloping, and then take a direct limit as the slope goes to infinity. That computes symplectic homology of V. Now, it will come up in a second, so let me put it up. We can also do this. We will denote by symplectic homology of V relative to the boundary. We're using these Hamiltonians, make them steeper and steeper downward and take a limit. That's also well defined. And the V-shaped ones are the following. We're using this one. So what are the generators of the Fleur complexes? So that we take limits where these go to infinity on both sides. Yeah. So what will we see? We will see periodic orbits on the boundary here. Of course, we smoothen this out. Yeah. So we will see periodic orbits on the boundary appearing here, running forward. We will see periodic orbits on the boundary here again, run backwards. And we will see critical points on the boundary. Yeah, so you see precisely the same generators as for the complex above there. If you do this. Oh, okay. We also see stuff here, but this stuff doesn't count. So to define it rigorously, we fix an action window, then we push this very high up. The way the action function is defined means the action becomes very negative and will be outside of whatever action window we fix, so they will not actually contribute. and only those will contribute. Yeah, that's how this definition works. And so this was the original idea. I think Alex came up with. He said, like, look, we can write this V-shaped temporal has exactly the same generators. Shouldn't it be the same thing? And then it is, yeah. But the proof is actually not trivial because it's very different Fleur problems. Yeah, very different action functionals to relate them. But this is true.
Is it true at chain level or?
No, it's not true at chain level. There's a whole bunch of deformations involved, and it's only true on homology. I think there's nothing true on chain level. No, because the Fleur complexes look totally different, and we deform really through a number of steps each time on the level of homology. I think there's nothing on chain level. We also not even writing a chain map from one to the other. We cannot. Yeah.
You don't write a chain, you don't construct.
We don't directly write a chain map,
So what,
which is commuting with the boundary, but we cannot.
what do you do?
What we do is we introduce a much larger class of functionals where we somehow allow here the Hamiltonian to take all kind of different shapes and also the Lagrange multiplier in there, and somehow show that there's a sufficiently large arsenal of functionals for which you can define Fleur homology, and it's independent of deformation. And basically in that class, we can deform from one to the other. And we have to prove compactness all along the way, that we're never losing compactness and things never escape to infinity. Yeah, so it's rather a continuation proof. Yeah. Okay, so this is one. And the nice thing about this is now we have an interpretation on an equal footing with symplectic homology. And this you can see as a complex for symplectic cohomology, actually, if you want, because this you can also dualize it, interpret as a complex for symplectic cohomology. And then when you stare at this, you may also see that there should be a long exact sequence connecting those three guys. So this is one statement. And the other statement is there exists a long exact sequence.
This is not a chain level thing. Do you mean, for instance, it fails to be chain isomorphic when you take over Z or something like that?
Oh, that I don't know. That I don't know. Yeah. I think this is beyond what we can do to answer this question. Yeah. So here we have a complex, and it goes from symplectic homology of V well boundary to symplectic homology of V to V-shaped symplectic homology of the boundary, and then there's a degree shift. And now this comes from a chain level short exact sequence, because you see, you look at this total complex. This total complex computes, you can deform to this one. This computes the symplectic homology. As a subcomplex, it has this one which computes the V-shape, and it has this one which computes this one. Yes, as a quotient complex, and then that's it. Yeah. So that is something more or less formal, that you have this long exact sequence. Yeah. And now you see that the terminology is kind of reasonable, because it looks like a sequence of the pair V, del V in cohomology. Yeah, this is due to our convention that we decide to call it symplectic homology and not cohomology. But it's actually related to singular cohomology. So this map here, and this will play a role, it actually factors through singular homology of V, well V, singular cohomology of V, and then going this way. So this map one can understand because it's something purely topological. It factors through something which is only living in the constant loop part, in the zero action part, and which you can. And this is part of the long exact sequence of the pair and singular cohomology now. Yeah, so that's a map you can work out in specific examples. Okay. So why is all this related now to anything about Poincare duality? Well, as I told you, this relative homology you can interpret as cohomology. That is something which Alex and I had observed a long time ago, that this is canonically isomorphic. There's nothing deep. It's also something purely formal to the cohomology of V. Well, likewise, this one would then be symplectic cohomology. Actually, it gets mapped. You do it appropriate. Should put it into negative degrees. Symplectic cohomology of V. Well, boundary. Let me also write this one. This will be symplectic cohomology 1 minus star of V again. Yeah. So that is something purely formal, and we were very happy with that. And somehow it never crossed our mind to complete this diagram. Yeah. So it was only after Nancy asked this question that in hindsight, something we should have realized years earlier, that, yeah, you see here, you have a sequence on cohomology again, right? So here's the sequence. What goes into here? You can just figure out by dualizing the upper sequence and then putting it below. Yeah. So what needs to come here is the V-shaped symplectic cohomology in degree 1 minus star. That is when you dualize the upper one and put it downwards. That is the thing that fits in there. So we better have an isomorphism here. Yeah. Now that thing is something interesting, because this is now an isomorphism from the homology of this space to the cohomology of the same space. Yeah. So this is really a self-isomorphism between homology and cohomology. So this deserves rightly to be called some kind of Poincare duality. Yeah.
And also, it seems by construction you have a map from singular cohomology.
Yes, I could also write the singular.
And you want that to be compatible with?
It's compatible. Everything is compatible then. I could write the singular homology picture down here also, and I could complete those sequences also. And yeah, so there's much larger diagram. Yeah, and everything is compatible. Mm-hmm.
What are the chains in symplectic homology?
The chains in symplectic homology. So, well, it's a Fleur homology. So it is it's critical points of the action functional for some Hamiltonian. Yeah, I should have maybe said that for the people who don't know that. You take the same function, but you don't have this eta, this parameter eta in it. You just drop the eta here. Then you get the Hamiltonian action functional. You take a Hamiltonian of this shape, and you count critical points of that functional in the Fleur theory sense. So those critical points are one-periodic orbits. You connect them by Fleur cylinders, and you do its Fleur homology. And then you take a direct limit as h goes to infinity. That is so the chains. So it's generated by one-periodic orbits of such a Hamiltonian. Yeah. So they are orbits which appear here near the boundary when you smoothen this out.
Commented. Have you proven, like you use, have you proven independence of filling, like some locality for this SH?
No, and in general, it does depend on the filling, but under some index assumptions, it does not. So you can understand in which that you can do a next stretching argument to try and prove independence of the filling, and if the Condescender indices are sufficiently high. I think something like Condescender index plus n minus 3 is always greater than 0. Yeah, so there's some condition on which it will actually be independent of the filling. Yeah, so that's, and this is relevant because actually a lot of examples fit into that. You get some interesting examples where it doesn't depend on the filling. But in general, it would depend. Mm-hmm. Okay. So one last comment, then I'll move back to loop spaces. Is so this is one way we could have seen that much earlier. Another way we could have seen it much earlier, even before this relation to symplectic homology, is in terms of the original definition here of Rabino-Wissler homology, because you kind of see an obvious duality here. Well, on the critical points, you have completely obvious duality. What is it?
What the eta is fine.
Mm-hmm. And
Change the direction of x.
yeah. You just run x backwards. and you put a minus in front of eta. Yeah. I mean, okay. So none of us has seen that, yeah. This has this obvious duality. That's a chain level isomorphism here, yeah, which induces this, and this is naturally giving you a chain map from homology to cohomology, if you think about it. Yeah, I mean, this okay. It needs a little bit of thought, but it's more or less it's obvious. Yeah, that this carries this duality in the original definition. Yeah. We still end up working more with this definition in terms of symplectic homology, because then it relates to these other variants of symplectic homology and symplectic cohomology, which is then useful for further study. But I think the Poincare duality isomorphism is most obvious in this original definition. All right, okay, so. So everything I was discussing about Rabino-Wissler and symplectic homology, we want to apply now to being unit disk cotangent bundles. So the cotangent vectors of norm less or equal to 1 inside of the whole cotangent bundle. That is our completed Liouville domain. This is the actual Liouville domain. Yeah. So we want to apply it to this setting. And what is the boundary of this? The boundary is the unit sphere cotangent bundle, vectors of length equal to 1. Yeah. So this is a nice Liouville domain with its boundary. We want to apply it in that setting. Okay, so let's let me just rewrite this long exact sequence, and let me maybe write it in terms of cohomology and homology. So we have symplectic homology of D star M going to symplectic homology of D star M going to E-shaped symplectic homology of the boundary going to homology in degree 1 minus star. So in this case, we know this one. Symplectic homology of the unit disk cotangent bundle, this is due to Viterbo and many other people, is equal to the homology of loop space. Lambda is the loop space of M of the underlying base manifold. Yes. So we know that. The same is true on cohomology then. Now this thing here is not something that has come up in the study of loop spaces at all. Yeah, so this we just give it a name. Yeah, so because this is a new player which has not appeared in string topology before. So let's just call this let's put a V-shaped thing here and just call it like this one. Yeah? This is just a definition. You could call this the Rabinowitz loop homology. Yeah? The Rabinowitz version of loop homology.
This is the definition.
Huh?
This is the definition.
That is the definition, yes. Yes, there is, but I will not have time to talk about it, I think, because I want to say some other things. Yeah, but I'll be happy to explain it. Yes, there is topological descriptions also of this. Yeah. Note, however, this is definitely not a homology of a topological space because this, by its construction, lives in arbitrary positive and negative degrees. Yeah, the way you think of when you see these generators, you have loops run forward and backwards. The ones tend to have positive degrees, the other negative degrees. Yeah, so it's definitely. But for example, you can construct it as a homology of a spectrum. Yeah. So it's not something that we have worked out yet. We're working on it, but we know it's possible. Yeah. Okay, but for now, I think for us, actually, this definition is quite convenient because we understand a lot about symplectic homology and rabinos homology. So it's actually not so bad as a definition. Yeah. Okay, so to understand this better, let's work out this map now. Let's give it a name for that to talk about it. This map C. As I wrote upstairs, it factors through singular homology. Now, in this case, it's easy enough. We can completely work it out. So this goes to singular. Well, okay. First of all, let me simplify. This map can only be non-trivial because this is homology of spaces. Yeah, and this lives only when star is greater or equal to 0. And this only when star is less or equal to 0. Yeah, so this whole thing can only have any contribution at all if star is equal to 0. Yeah. So let me immediately restrict to that case because only then do you have anything non-zero. Yeah. So what do you get when star is equal to 0? Then here you get upper n of v rel boundary. It's d star m rel the sphere bundle. Now you remember your algebraic topology. Yeah, so this is Tom isomorphism. This is H upper 0 of M. This by contractibility is H upper n of M. And down here you have the Giesing sequence. So which means that here you have multiplication by the Euler class. Yeah. Or yet in other words, if M is oriented, say, then this is the integers, and this is just multiplication by the characteristic of M. Very good. So, which means that this log exact sequence almost splits. Yeah. Because this map here, for example, if the Euler characteristic is 0, then this is a 0 map, and then actually the log exact sequence is a short exact sequence. Then it's just 0. Yeah. If it's not 0, let's just mod out this tiny bit here and define a reduced version so that it actually splits. So we get a short exact sequence when we replace this one here by the co-kernel of C. Here we have. Here we take the kernel of C. Now we just make it split by brute force, yeah, because we pass to the co-kernel and kernel. But we're not really doing all that much, yeah. We're just modding out. We're modding out Euler characteristic times the class of a point. Yeah.
Can you repeat why that thing contributes only when star is 0?
Yes, because this is the singular homology of loop space. This exists only when star is greater or equal to 0. And this is singular cohomology of loop space. It exists only when the degree is greater or equal to 0, which means star must be less or equal to 0 because it's minus here. Yeah.
What is the vertical map there? That's the
inclusion of constant loops.
Okay, that's it?
Yes.
Oh, okay.
Induced by inclusion of constant loops. which somehow funnily, because one is homology, one is cohomology, they go in opposite directions. So it somehow nicely makes this one go around like that. Yeah. Yeah, here's just so the map from here to, wait, how do you say that? Yeah, from here to there is literally just inclusion of constant loops into all loops. Well, why is that degree shift now? Maybe I should use Poincare duality once again to convert this to H0, H lower 0 of M, and then it's inclusion in H lower 0 of lambda. That's just inclusion as constant loops. Yeah. So it's just that. Okay, so this one, let's just call this the reduced loop space cohomology. No, sorry, this is homology. And this is reduced. So it's not as in topology. Reduced means you do it relative to the class of a point. Now here we do it relative to Euler characteristic times a point. Yeah. So when Euler characteristic is 0, we're not modding out anything. Then it's just the usual thing. Otherwise, we just model. Yeah. So when we work with Z coefficients, we actually create some torsion here. Yeah. So this is somehow our adjusted version of reduced. Yeah. Okay. So which means that this is roughly the direct sum of loop space homology and loop space cohomology. Yeah. One sitting in the positive degrees, the other one sitting in the negative degrees. So now, what about products?
Can you actually have a shift then, or?
Yeah, there's a shift. There should be a shift.
Oh, yeah.
I'm fairly sure I did it right. Yeah. Yeah. So there's no shift here, but here there's a shift by one. So and so next thing. So we have this long-leg sequence. Now this is something actually which I could say in the general section. This is true for every rabinos Floer homology. On this one here, we have a pair of pence product. Let me call it M. Because this is defined as the Floer homology of some Hamiltonians. And you do the usual construction of the pair of pence product, and it gives you a pair of pence product also on this rabinos Floer type complex. Yeah. Now on the usual symplectic homology anyway, you have a pair of pence product. So here also. Now that pair of pence product is known to correspond here to the loop product. Yeah. That is Abundantolo-Schwarz. Yeah, that the pair of pence product on Floer homology of a cotangent bundle corresponds to the loop product on the loops space homology. Okay. So what we have here, if I put it over here, is we have a pair of pence product here. So we denote M to distinguish it. Here we have the usual loop product, and okay. And this is a ring map. That is, yeah, just, this is also always true. This is a ring map. Now, what about coproduct? Now there's a natural guess, yeah, that maybe the coproduct should naturally live here. Yeah, the loop coproduct. Well, you see, the loop coproduct is a coproduct on loop space homology. If we dualize it, because here we are in loop space cohomology, we get a product on loop space homology. Yeah, dual to it. Also note this had degree minus n, this had degree 1 minus n. But we have a degree shift here by 1. So it precisely compensates. So all these guys have the same degree now, if you do the degree shift here, which somehow comes naturally out of the non-exact sequence, yeah? So it all looks right, yeah? So it just wants to be true, and it is. So here in, well, in good cases, it's not how a theory should start, right? And it might be that it's enough to assume that H1 of M is equal to 0. But we need to check exactly under what conditions. But in good cases, this short exact sequence splits. This sequence up splits as a direct sum. So we can somehow find the splitting map to write the middle one as a direct sum of the other one. So the V-shaped space homology is becoming a direct sum of these guys, such that this product here, this one restricts to the loop product here and the dual of the loop product of the loop coproduct there.
Are the cross terms or?
And there are cross terms. So those two guys, in good cases, are subrings, meaning when I plug in two elements here, I get an element in here and likewise here in this big product here. But there are mixed terms. You can plug in something from here and something from there and get a non-trivial product. Yeah. So it's not a direct sum of rings.
Is Euler characteristic 0 a good case? Or?
No. No. So good case is, and I think that's probably also what I'll stop with. A good case is M is Sn n greater or equal to 2, and the bad case is M equals S1. That case costs me a lot of headache. You were there when I suffered at Mittag-Lechner Institute a year ago and tried to understand the S1 case. I think by now we more or less do understand, but it would be a separate talk. Let me add one more thing. Now, coming back to Sullivan's relation and Sullivan's So now the mu and lambda appear as components of this big product, right? Now the amazing thing is Sullivan's relation comes out as part of associativity of this big product. Yeah, that's a good question. Yeah, and that's it's actually no. It's this I can answer because mu and lambda both live on reduced loop space homology. Now, yeah. So this also answers my second question from the beginning, or my first one. Can I put them on an equal footing? Can they find them on the same space? This is the space. So part of this statement is the product actually descends to this reduced homology where mod out Euler characteristic times a class of a point.
So you don't mod out constants, you mod out Euler characteristics.
Yes. I convinced you with this torus example, I cannot mod out all the constant loops. Then the product doesn't descend. But there in the torus case, the Euler characteristic is 0. Yeah. So okay. I mod out Euler characteristic times a point. I'm not modding out anything. It's fine. Yeah. and the other part of the claim is the coproduct can actually be defined also once I mod out Euler characteristic times a point. I don't have to mod out all the constants for that. So this is exactly the thing I need to mod out so that both operations are defined on that space. And then they satisfy Sullivan's relation on that space. Then Sullivan's relation makes sense. And it comes, I mean, you can prove it directly also, but it comes as part of associativity of that product, which that is actually something very general because we know the pair of pants product in free homology is associative, just on very general grounds. Yeah. So basically that gives us Sullivan's relation here, just without any additional proof.
I'm just confused. So Euler characteristic for the torus is 0, but if I thought it didn't work for the torus.
No, I showed you I cannot mod out all the constants. I can mod out Euler characteristic times a point class. Yeah, because then I'm not modding out anything there. Okay. I mean, what I did not show you is that it's part of the claim for the torus. I could also define the coproduct now, not modding out anything. So this problem with the additional boundary terms, the claim is you can somehow make them go away. The way is you deform the definition by choosing a vector field. Euler characteristic 0, you choose a nowhere vanishing vector field and you deform it by pushing the condition. So the condition was the evaluation at time 0 and evaluation at time A should coincide. I mean, you don't make them coincide, but you say one should be the other one times the time 1 map of some small vector field, which is nowhere vanishing. And then it works. Yeah. But it's also something that we only saw after we went through this whole Rabinowitz mumbo jumbo, and now at the end of the day we can say directly in topological terms, yeah, what needs to be done, and that works fine. But it actually does not work for S1, although the Euler characteristic is 0. So you can define it, but it doesn't satisfy Sullivan's relation. So there is more interesting stuff going on, and I could keep going on, but time is over. So thanks a lot. And
so what are other bad cases besides S1?
Well, that's the only case we can compute, so I don't know.
But you know, so you don't have an idea. What?
Well, probably high dimensional tori would be as bad. Yeah. The TN should also be a bad case. But beyond that, yeah, we don't know.
We have a fix in that case?
Yes, but the fix is somewhat more complicated. So it turns out, and that costs us a lot of headache, is I think now we believe the correct fix is that in that case, you can still define this product, and but Sullivan's relation would need to be modified. So you get something, but it's a generalization of Sullivan's relation. So I think we can write down some more general relation, which in the good cases would just become Sullivan's relation, but it would cover all cases, but it has an extra term in Sullivan's relation. Instead of 3 terms, Sullivan's relation would actually contain 4 terms. There's a 4th term that needs to be put into Sullivan's relation, and then I think it's always true. And then it's just becoming a special case of that in these good cases somehow it's becoming the original Sullivan's relation. I think that's our conclusion as of now. Sullivan's relation might not be the correct thing to ask in general. Yeah.
And similarly, like associativity is equivalent to the Sullivan's relation.
We haven't checked that, but probably so. Yes, probably that should maybe. Well, that I'm not sure. I mean, in those bad cases, we also don't have this nice split. I mean, of course, if we choose field coefficient, it always splits. But the splitting is not canonical. We might not have. I think we probably don't have that statement that the product restricts to these here and makes those subrings. This will also not be true. I think this splitting is also something which will not be true in the general case. So the picture gets a bit more, gets a bit more complicated in the general case. But I think we have a picture that works in all cases.
Any questions?
I can actually ask this, but like, do you actually realize this as a cone of some map of spectra or something like that? You mentioned some Lifton spectrum.
Yes. Let's discuss it separately because this is somehow it's been a long time that I haven't thought about this aspect. And I hope we can ask. Yeah.
Okay, if there are no other questions, let's thank the speaker again.